Hello guys! For today's lecture video, we will discuss a brief overview of the historical background of quantum mechanics. We will explore on the key discoveries and challenges that led to the birth of quantum mechanics, fundamentally changing our understanding of the universe. If you're a physics enthusiast or student, you might have asked yourself, how did quantum mechanics begin? What led to the development of this groundbreaking field and why was it necessary? So, quantum mechanics emerged in the early 20th century as a revolutionary response to the limitations of classical physics. Classical theories like Newtonian mechanics and Maxwell's equations successfully explained many natural phenomena but fell short when applied to the microscopic world of atoms and subatomic particles. So, learning quantum mechanics is not just another chapter in physics. It represents a profound shift in how we think about nature. It requires a strong foundation in advanced mathematics as it involves complex concepts just like wave functions, probability amplitudes, and operators. So, mastering these mathematical tools is essential for students eager to explore the mysteries of the quantum world. So let us recall first the grand unification which occurred with the advent of Newtonian mechanics. So here, this unified the physics of terrestrial and celestial bodies under a common framework. So the Newton's laws of motion and universal gravitation explained a wide range of physical phenomena. So from falling apples to planetary orbits. However, Newtonian mechanics began to show limitations when applied to systems at very small scales, just like atoms, and at the very high velocities near the speed of light, or in the presence of strong gravitational field. So, these limitations of classical physics eventually led to a significant problem or crisis during that time. Now, the ultraviolet catastrophe in blackbody radiation was a major crisis during that time. Classical physics could not explain why the energy emitted by a blackbody didn't go to infinity as the wavelength is decreased. So, let's have some illustration of a blackbody. So, let's take a look at this closed volume or system with completely sealed walls, which is perfectly reflective on the inside like mirrors. Now, if we poke a hole through one side of the volume or the system and let the energy come in, so eventually the system settles in a state of thermal equilibrium. So when we say it's thermal equilibrium, it means that energy throughout the system is evenly distributed. So here, the volume or system will do two things. First, it will absorb light from the whole electromagnetic spectrum. And secondly, it will also emit light at varying frequencies. And this is called the black body. So, basically, a black body is an idealized physical object that absorbs all incoming radiation or light and emits radiation at all wavelengths. So the emission of this radiation depends only on the temperature of the black body, not its material or surface properties. Say for example, here, this picture. As a black body gets hotter, it shifts from emitting mostly infrared light. So I have here the electromagnetic spectrum, and we have this radio wave, microwave, infrared, visible, ultraviolet, X-rays, and gamma rays. So this is the wavelength, and longer wavelength entails lower energy, and shorter wavelength entails higher energy. Say, this is the reason why a metal rod glows red when heated and then turns yellow at the tip as it gets even hotter. So you can see here that red and yellow, here we can say that yellow here is much hotter since it has a shorter wavelength compared to red. And so if we examine this spectrum, color indicates the energy and temperature of the radiation being emitted. And the law of thermal radiation states, this is from Gustav Robert Kirchhoff in 1860, and it states that any object at a temperature above absolute zero emits electromagnetic radiation. The amount and type of radiation emitted depend on the object's temperature and surface properties. And according to Wien's displacement law in 1893, it states that the wavelength at which a black body emits radiation, this is most strongly, so this is the peak of the wavelength given by the lambda peak, and this is inversely proportional to its temperature. So the mathematical form is given by this equation, and this is the peak wavelength, and T here is in Kelvin temperature, and B here is the Wien's constant. And the relation to the black body radiation, this law explains why hotter object emits radiation at shorter wavelength. So again, as a black body heats up, it shifts from emitting from infrared, this is the infrared region, to visible light, and then the ultraviolet as the temperature increases. So we have here the classical prediction. So in classical physics, using the Rayleigh-Jeans law, it predicted that as the wavelength of the emitted radiation decreased, so we can see here the graph, wavelength versus the radiance, spectral radiance. So as the wavelength of the radiation is decreased, the intensity should increase indefinitely, as you can see here at the black line. So this means that at shorter wavelength like UV, so the emitted radiation should become infinitely strong as the wavelength approaches zero, and this would result in a catastrophic amount of energy, which obviously does not happen in reality. So this catastrophe refers to the absurdity of this prediction. So it suggests that a black body at any temperature would emit infinite energy. So particularly in the UV and even higher frequency regions of the spectrum. And this clearly contradicted experimental observations. So this one. So where the intensity of radiation does not keep increasing indefinitely at shorter wavelength. Instead, it rises to a peak. So as you can see here, the blue, the green, and the red line. So it rises to a peak at a certain wavelength, and then it decreases. Especially at the UV spectrum. Okay? And this was a significant discrepancy that classical physics could not explain. So we have here in 1896 the Wien's distribution law. It was derived empirically and describes that spectral distribution of black body radiation at short wavelength, meaning short wavelength, high frequency, and it successfully explains the intensity of radiation emitted at shorter wavelength but fails at longer wavelength. So we can see on the next slide about this graph. And the Rayleigh-Jeans, this is the formula, and it was derived using classical physics and describes the spectral radiance of a black body radiation at long wavelength, meaning low frequency. And according to this law, the spectral radiance should increase indefinitely as the wavelength decreases. So the main solution for this is when we have Max Planck, and he proposes a solution for this. And in 1900, Max Planck proposed a revolutionary idea to resolve this UV catastrophe. He suggested that energy is not emitted continuously, but in discrete packets called quanta. And the energy of this quanta is proportional to the frequency of the radiation. So here, if you are very familiar with this equation, E is equal to energy of the photon is equal to Planck's constant H times the frequency. Okay, and here, by assuming that energy levels are quantized, Planck could correctly predict the observed spectrum of a black body radiation, and his formula matched the experimental data across all wavelengths, including the ultraviolet region. And this is a big impact on physics. So, the Planck solution marked the beginning of quantum theory, and it introduced the concept of quantization, which was later expanded upon by other physicists like Einstein, Niels Bohr, and which leads to the development of quantum mechanics. So we have learned that Planck's idea is the start of the shift from classical to quantum paradigm. Okay, so Planck introduced the idea that energy is quantized. So meaning it can only be emitted or absorbed in discrete amounts or in quanta. So Planck's quantization of energy bridged the gap between the Wien's law, accurate at short wavelength, and Rayleigh-Jeans, accurate at long wavelength, by introducing quantum mechanics into the description of a black body radiation. So quantization, that's why we have the word quantum mechanics. So here, if we study this graph, this is the graph frequency versus the intensity. So according to classical physics, this is the Rayleigh-Jeans. This is the classical approach, this line. So as the frequency of electromagnetic radiation increase, the intensity should increase indefinitely, towards the ultraviolet catastrophe. While in quantum, this is the quantum graph, and this curve where intensity increases with frequency to a certain point. So there is a peak and then falls off. This accurately describes the behavior of a black body radiation. So here, we have here this graph. This is Rayleigh-Jeans, the black one, blue one, the Planck, and Wien, the pink. So here, the Wien's distribution law works well at shorter wavelength but fails at longer wavelength, while Rayleigh-Jeans law works at long wavelength but predicts an unphysical infinite energy at short wavelength, leading to the UV catastrophe. And this UV catastrophe, I would like to highlight that this is the failure of classical physics that led to the development of quantum mechanics. So thank you to Planck's law, which provides the correct description of a black body radiation across all wavelengths. So this is now the start of the birth of quantum mechanics. So classical mechanics describes the motion of macroscopic objects. So while quantum mechanics is a fundamental branch of physics that deals with the behavior of matter and energy on the smallest scale, for scale of atoms and any other subatomic particles. And this is the start of the shift from deterministic to probabilistic approach. So here you can see at the illustration, this is a classical system where energy changes smoothly and continuously. So just like this ramp, you can move up and down. So if you imagine pushing a ball up a ramp, and it can stop at any height along the ramp, reflecting any possible energy level. However, this one in quantum approach, so energy levels are quantized. So we can illustrate this like a staircase wherein particles can only occupy specific or discrete energy levels. So, where you can stand only on the steps, not between them. So, the idea of Planck's hypothesis was supported by Albert Einstein through his ideas in 1905, and also this is his idea where Einstein won his Nobel Prize, explaining the photoelectric effect by proposing that light itself is quantized into particles called photons, and provided more evidence for quantum theory. So, as the quantum theory evolved, it introduced the idea that particles, like electrons, could exhibit both wave-like and particle-like properties. So, these dual properties was essential in understanding the behavior of subatomic particles and led to the formulation of quantum mechanics by Heisenberg, Schrödinger, and others. And over the following decades, quantum mechanics became the fundamental framework for understanding atomic and subatomic phenomena, leading to numerous technological advancement, which includes semicon, lasers, and quantum computing. So, here, as a closing, the transition from classical to quantum physics is often referred to as the quantum revolution, which fundamentally altered our understanding of nature, leading to new fields of study like quantum field theory, quantum electromagnetic and beyond. So, thank you for listening to this short lecture video. Till next time. Thank you.